So with that, I'd like to turn it over to Jim. And if you have anything else to add about your background, Jim, have at it.
All right, thanks, Chuck. I'm just going to share my screen now. Hopefully everybody can see that. So I'd like to start by thanking Chuck for reaching out and inviting me to present this evening. It's my pleasure to share what I've learned about filters with the amateur astronomy community whenever I can. Chuck already gave kind of a brief overview of my background. I am an aerospace engineer by education. My background is primarily in propulsion and aerodynamics. Since I graduated, I've been working for a defense contractor here in the Ottawa area called Davis Engineering. And we design and build infrared suppression systems for ships and aircraft, so a lot of defense-related stuff. I live in the Ottawa area, right basically downtown Ottawa, with my wife and 2 kids. And the sky in my backyard is a nice milky Bortle 9+. I grew up keenly interested in astronomy, but I didn't pursue it actively through my 20s and 30s. There was simply too many other things demanding my time. But around 2009, my kids started getting interested in astronomy, which in turn invigorated my interest in the hobby again. Over the past 10 years or so, my interests have really focused on astronomical filters, inspired largely by my bad light polluted skies and the unwillingness of myself to accept that there's a general lack of useful information on filters available in the public. My plan this evening is to share much of what I have learned over the years about filters through research, analysis, and testing. Everybody can see the slides okay? I didn't get any positive feedback there.
They seem to be coming across quite well.
Okay,
they look good.
Excellent, thanks. So my talk tonight is organized into 3 main parts. The bulk of the talk will be taken up by discussing what they are and how to use them. And then at the end, I will present a brief summary of some of the latest research I have been working on. So without further ado, let's get started with part 1. What are they? Here we see a lovely image of a mountain valley, rich in detail and contrast. Unfortunately, more often than not, something gets in the way of us capturing the view that we want. This is where a filter comes in. Their purpose is to block light we don't want to see. By doing this, we can improve the contrast and sharpness of our view, emphasize specific features in the scene, or help enhance faint details. To give you an idea what I mean, consider this view of the planet Mars. This is what it looks like to the Hubble Space Telescope. From our vantage point here on Earth, however, the view is not quite as nice. Our atmosphere hides details from view. We can, however, add a color filter to improve the view. For example, adding a red filter will darken greens and blues, increasing contrast. Similarly, a green filter can enhance the visibility of other parts of the planet's surface. The same is true of a blue filter, which can enhance the view of clouds and polar ice caps. Another example of what filters can do applies to deep sky objects. This is an image of the Flame and Horsehead Nebula taken from my backyard with no filter. Although the objects are visible, contrast and detail is poor. Now, add a light pollution filter, And you can see a marked improvement in the scene's contrast and detail. There are essentially two types of filters. The first type are most commonly referred to as planetary filters, which are in essence color filters, commonly identified using the Ratten numbering system. These filters are all absorption type. They block light by absorbing it. The other type of filter goes by several names, including deep sky, nebula, or light pollution. Regardless of the name, these are all interference type filters. They block light by reflecting it. I will explain more what I mean in a moment, but first, let's take a moment to talk about special filters. There are filters on the market that combine both absorption and interference for very specific applications, such as planetary observing, chromatic aberration correction, solar observing, and UV IR blocking. Although these are also very useful filters to the amateur astronomer, let's ignore them for now. Getting back to how filters work, consider this graphical representation of an absorption type filter. These filters consist of dye-infused glass or a colored gel that is sandwiched between two thin layers of glass. Molecules in the dye are designed to absorb some wavelengths, but not others. The result is a filter that can selectively block light, but in a rather imprecise way, in broad bands with gently sloping cutoffs. By the way, if you were wondering where Ratten numbers came from, Frederick Ratten was a British inventor and co-founder of the first photography company. He devised a standard catalog of filters for use with terrestrial photography. He and his partner, C.E.K. Mies, sold their company to Eastman Kodak in 1912. Kodak still manufactures Ratten filters to this day. Interference filters are rather different than absorption filters. They are made by adding tens to hundreds of thin alternating layers on a glass substrate. Each layer is made up of different materials with varying refractive indexes. At each boundary between layers, light partly reflects and partly refracts. By choosing the thickness of these layers, it is possible to have all the reflections of undesired wavelengths out of phase with itself, so they cancel out, allowing only the desired wavelengths through. Interference filters made more than 10 years ago tended to sandwich the layers between clear glass, just like color filters, because the refractory materials were relatively soft. Now the materials used are harder than the glass substrate itself and do not need to be protected. For the next couple of slides, I will describe some commonly used terminology. The first being the idea of a spectrum. A spectrum is a quantitative visual way of presenting how well a filter transmits light at different wavelengths. The example spectrum shown here is the typical format for presenting filter spectra, with wavelength on the horizontal axis and percent transmission on the vertical axis. It allows for easy comparison between filters and provides information on how the filter will perform in different situations. The next term to discuss is luminous transmissivity. %LT is essentially a measure of generally how dark a filter is. On average, what percentage of light is getting through. It is calculated based on the specific sensor the filter is being used with. So a filter will have a different %LT value if it is used with the human eye as opposed to a camera. For whatever reason, it seems that the value of %LT that you sometimes find quoted on a manufacturer's website is the value for daytime human eye use. For those interested, the actual calculation of %LT is simply an average where the filter transmissivity at each wavelength is weighted by the sensor sensitivity at the same wavelength. The next item I'd like to go over is some basic filter nomenclature. This filter spectrum plot is for something called a low pass filter. All the light at wavelengths below the cutoff are passed, and all those above are blocked. The opposite of this filter is a high pass, where all wavelengths above the cutoff are passed and those below are blocked. If we combine these two spectrums together, we get a bandpass filter. In this case, a wide bandpass. This spectrum type is defined by its center wavelength and its band width, also referred to as its full width half maximum. The full width half maximum is literally the wavelength width from one side of the band to the other, with the cutoff wavelengths placed where the transmission value is half of the maximum. Bandpass filters can come in any width, from wide, like the one shown here, to narrow. It is also possible to have more than one passband. This, for example, is a multi-narrowband spectrum, which I will discuss more about later. The idea of multiple bands can be taken to the extreme. With filters that have so many passbands, they are sometimes referred to as comb or notch filters, due to the shape of their spectrum. I refer to these filters simply as multi-band pass. Now that we have some filter lingo under our belt, let's look at some actual filter spectra, starting with absorption type filters. Blue and green filters all tend to be wide bandpass filters. Yellows, oranges, reds, and infrareds are all high pass filters. Pinks and purples are a combination of bandpass and high pass that block green. Browns are high pass filters with some additional green and blue added. All of these filters have gentle cutoffs and relatively low peak transmissivity values, typical of absorption type filters. Color filters with steep cutoffs and high transmissions are available, but they are all a combination of absorption and interference types. Most of the interference type filters made for astronomy are for use with deep sky objects. They are designed to selectively pass desired emission wavelengths from nebulae, namely hydrogen beta, O3, hydrogen alpha, nitrogen 2, and sulfur 2. The thing that distinguishes one filter from another is the extent to which it blocks light pollution. In an attempt to make some sense of things, I have created my own Deepsky filter categories. Probably the most common category is broadband. These filters have a single large passband around hydrogen beta and oxygen 3 and are meant for visual use. They therefore do not necessarily pass hydrogen alpha. I have, based on bandwidth, further subdivided the category into extra wide, wide, medium, and narrow. The next major category is narrowband. These filters have a single narrow passband around one of the nebula emission bands of interest. Hydrogen alpha, nitrogen 2, and sulfur 2 filters are only for imaging, as our eyes cannot see these wavelengths when dark adapted. Narrowband filters in the 10 to 20 nanometer wide range are typical for visual applications, and less than 10 nanometers wide are meant for imaging. The next major category is multiband. As discussed earlier, these filters pass multiple bands and tend to block specific wavelengths known to predominantly contain light pollution. Overall, their ability to block light pollution is moderate to poor, but they do a very good job at providing a nice color-balanced image. They are less effective around modern LED lighting due to their passing a lot of the blue part of the spectrum. The final Deepsky filter category is a relatively new one that I call multi-narrowband. These filters have narrow passbands around more than one nebula emission. They are often referred to as dual, tri, or quad band filters, depending on how many bands they pass. They are designed to maximize the amount of light pollution blocked and have recently become very popular with astrophotographers who use them with one-shot color cameras. So this concludes part 1 of my presentation. If there are any questions on this material so far, I am happy to answer them.
Yes, this is Brian Smith. The question I have is, when you're using these filters, don't you want to separate out the bands and not have them all in the same band range for like oxygen, hydrogen?
You're referring to the filters like the multi-narrowband that passes more than one wavelength of nebula emission?
Right. If you had one
Yeah.
filter and you want oxygen 3 and then you want to look at hydrogen, but if they're both at the same bandwidth, wouldn't they be canceling out each other? Or
Yeah, so certainly if you are using the filters for visual observation, you would end up getting the two emissions, the oxygen 3 and, well, you can't see hydrogen alpha, but say hydrogen beta and oxygen 3 for visual use, they would add on top of each other. So you would get a combined image and you would not be able to distinguish between one emission and the other. It would just be one combined emission.
okay, that answers my question. Thank you.
Yeah. To add just a bit to that, if you're using a camera, like a one-shot color camera that has blue pixels, green pixels, and red pixels, the camera can actually distinguish to some extent the emissions, because the red pixels only pick up the hydrogen alpha emission and the blue and green pixels only pick up the oxygen 3. So that's why the multi-narrowband are becoming popular, because you can collect and separate the signal from two different emissions with one camera in one exposure. Any other questions on this section before we move along?
Yeah, I have one. This is Chuck Riel. Um, in a general sense, is there any trend at all to use digital filters as opposed to analog type filters like this? I know they're used in remote sensing, and you're able to have a digital representation, of the filter response like the ones you've been showing. And it's all done internally in a digital framework.
Yeah, the difference is the manner in which the data is being collected. So the way the eye and the camera is collecting the light and then putting it into a form that can be used, it's already integrated. All the wavelengths are integrated together in time. So it's not like electrical signal where you're able to sample it in time and you have it you can analyze it kind of in the frequency domain. I don't know if people know what I mean, but it's the way the data is managed. The time aspect of the data is lost once it's been perceived by the eye or a camera. So you can't apply a digital filter. The only way to filter out particular wavelengths is to do it optically.
Okay, thank you.
I have a question for you, Jim. This is Brian. These multi-pass narrowband filters, these tri-band filters, I understand that they negate a lot of the negative part about narrowband imaging with a one-shot color camera, because typically, and I'm just want to make sure I understand this correctly, typically if you used a single band, right, the dog starts to bark right when I talk. If you use a single band like hydrogen alpha on a one-shot color camera, you're using 1 pixel out of every 4. If you're using a tri-band, you're getting that hydrogen, or you're getting the hydrogen alpha in the red, but you're getting the oxygen 3 and maybe some of the sulfur. I don't know. That's a question I have. Using the red and green, the green and blue pixels. So you're utilizing more pixels at a time, therefore, more efficiently grabbing the photons. Is that largely correct? That's the first part of that.
Yeah, that is correct. Okay. You are simultaneously using more pixels to collect image data. Yeah.
So my question, based on that, and as a person who has just kind of gone down the rabbit hole of monochrome cameras, how much of that do you feel, and I know it's subjective in your opinion, negates a lot of that benefit? I know you probably still have more sensitivity. You have specialized filters on that mono camera. How much that do you think negates a lot of the benefits of a mono camera over a one-shot color?
Well, the one thing that you're still missing out is resolution. So even though all of the pixels are collecting image data, you still only have a quarter of the pixels collecting H alpha data. So the resolution that you are getting is a quarter of what your sensor's resolution actually is.
Right, the Bayer filter's kind of faking that resolution. But you end up with the same resolution, but it's using an algorithm to kind of figure it out, to borrow.
Yeah, and it's not the same. It's doing its best guess to fill in missing information, which is not the same thing as actually measuring the real signal. So you definitely see an improvement in resolution.
I definitely noticed that. The clarity seems to be there on the mono. So you're getting the light, but it's not necessarily matching it up perfectly. It's kind of fudging it a little bit, I guess.
Yes, exactly. You're essentially, you're almost subsampling the image and then blowing it up again to the full scale. So you're not actually, you might have a 10 megapixel camera, but not all 10 megapixels are being used to resolve in each of the bands. So that is the one of the main advantages of monochrome, is that you're using all of the resolution of the sensor to collect spatial information in each individual band.
I guess supposedly if you want to do some type of monochrome, look for exoplanets or things like that, you're going to really benefit from the monochrome camera because you're not really looking for color. Okay,
That's right.
thanks.
Yep. Okay, if there aren't any other questions on this section, we'll move along into part 2. So let's open the discussion about how to use filters by starting with solar system observing. Recall that these filters are used to darken some features, but not others. This is accomplished primarily using absorption type filters. What filter to use is, unfortunately, very subjective. There is a lot of trial and error required, and in the end, it comes down to personal preference. If you like to read astronomy books or find online resources that will tell you the best filter to use for observing the planets, the end result will be a list as long as your arm of the filters you simply must have in your kit. The alternative is to take the advice of a poor schmuck who actually took the time to test all of these combinations for himself. Personally, I have found most filters do very little to improve the view. The list of filters that actually do something significant to the view, in my opinion, is short. On Mars or Jupiter, a magenta filter like a Raton number 47 or a number 30 does a good job of enhancing contrast. A red filter on the Moon or Mars also works well to sharpen the image and improve contrast. A light tan or orange filter like a Raton number 81 or number 85 is also beneficial in enhancing details in the bands on Jupiter and Saturn. If you often observe a nearly full moon or Venus, you may also want to use a variable polarizer or neutral density filter to cut down the brightness. If you are lazy like me and just want one all-purpose filter for planetary observing, you may want to consider a special type filter called a moon and sky glow, or more generically, a neodymium filter. One final thing to remember is that filters block light, so your view will be darker. Dark filters, those with a low value of %LT, may require a large scope to use effectively. For those of you who are imaging solar system objects, contrast, color, etc. can all be controlled after the fact during post-processing. So a color filter is not needed. The main concern is seeing. The unsteadiness in the view resulting from turbulence in our planet's atmosphere. At a minimum, you should use a UV IR cut filter to sharpen your view. Or try filters passing red or infrared only, as seeing has less of an impact at long wavelengths. Again, a good all-purpose filter for imaging exists. The moon and sky glow I mentioned earlier does a pretty good job of cutting UV and IR and enhancing contrast. Moving on to deep sky observing, let's review again what sort of benefits can be realized when using a filter. This is a sketch I made of M42 from my backyard in Ottawa using a 4-inch refractor. Without a filter, all I could make out was a smudge of nebulosity around the trapezium stars. Adding a medium broadband filter improved the contrast and allowed a bit more of the features around the perimeter to be visible. Moving to a narrowband oxygen 3 filter resulted in a large improvement in the amount of faint structure that I could see. Finally, the multi-narrowband filter gave the best view, with subtle differences in the brightness of the features now being visible. The impact of different filters can also be visualized using imagery. This is an image of the North American Nebula captured from my backyard using that same 4-inch refractor. With no filter, it is difficult to make out the nebula amongst all of the many Milky Way stars. Adding progressively narrower filters from wide broadband to medium broadband brings out more and more detail in the nebula. You will also notice that the stars are becoming progressively fainter. Adding a UV IR cut filter to the medium broadband further increases the image contrast. Further improvement in contrast is achieved by moving to progressively narrower band passes. First, a multi-narrowband filter, and finally, a narrowband hydrogen alpha. Note that all 6 of these images have the same total exposure time of 5 minutes. So, how does one choose what deep sky filter to use? Well, like planetary filters, we want to increase contrast, and the interference type filters are the most capable of delivering accurate, high transmission passbands around our wavelengths of interest. The best filter to use depends on a number of things, including the nature of your light pollution, the type of deep sky object you are trying to observe, the size and type of optics you are using, and in the case of imaging or electronically assisted astronomy, the tracking capability of your mount. The next couple of slides discuss these factors in more detail, starting with light pollution. Light pollution is all the light entering your telescope from sources located between us and the deep sky object. The most obvious source of light pollution comes from man-made outdoor lighting, some of which illuminates our view directly, and some illuminates the sky by scattering off dust and moisture in the atmosphere. There is also a naturally occurring component of light pollution, generally referred to as sky glow. This light is emitted by atoms in the Earth's upper atmosphere that were energized by the sun's UV rays during the day. The final naturally occurring source of light pollution is, of course, the moon. It acts like a big mirror, reflecting the sun's rays back at us, thus giving it a broad light spectrum. As suggested by the component spectra shown on this slide, light pollution consists of both broadband and narrowband emissions. To understand the implications of this on our filter choices, we next need to have a look at the spectra of deep sky objects. Deep sky objects can be grouped into 2 categories based on the nature of the light they give off. The first category is broad spectrum objects. This includes galaxies, star clusters, and reflection nebulae. Basically, anything that we can see because of light emitted from stars. The fact that these objects have broad spectrums makes them very difficult to pick out from light pollution using a filter. The second category of objects are narrowband emitters. These objects include hydrogen-2 regions, planetary nebulae, and supernova remnants. Any object that we can see because of light given off by excited gases like hydrogen or oxygen. Because these objects emit at very specific wavelengths, they are much easier to separate from light pollution using a filter. The last thing to consider before choosing your deep sky filter is telescope aperture. Recall that filters block light, resulting in a darker view. This means that the percent LT of a filter will limit the aperture of scope you will be able to use it with visually. This plot provides a general recommendation for how dim a filter you can use with different sized scopes. At the top, I have marked off the ranges of percent LT that are common for the different categories of deep sky filter. So, for example, if you wanted to use a typical medium broadband filter with a 4-inch refractor, you'd probably be okay. Trying to use a narrowband filter with a 4-inch refractor is probably pushing your luck. For imaging, or EAA, there is no such limit on scope size because you can simply compensate with more exposure time. This does, however, mean that you will need progressively better mount tracking the narrower the filter is you want to use. There is one final thing to note in regards to aperture. The impact of a filter on broad spectrum objects is much worse than for narrowband objects. At last, we have come to where the rubber meets the road. What is the best deep sky filter to use? If you are observing or imaging a narrowband object, the best filter to use is the narrowest bandpass filter your aperture or mount tracking will handle, regardless of how much light pollution you have, be it Bortle 2 or Bortle 9. Adding an IR cut filter can also help to improve contrast if using a camera. If you are observing broad spectrum objects from a dark sky, don't use any filters for visual observing. If imaging, an IR cut filter can help contrast, but the improvement is small. If visually observing broad spectrum objects from a light polluted location, yeah, I'm afraid there isn't a filter that can help. If using a camera, however, a wide to medium broadband filter that passes infrared works best. Even better contrast can be achieved using an infrared high pass filter, although very long exposure times will result. I have one additional thing to note about trying to image in infrared using a refractor. Most ED doublets and apo triplets are okay, but achromats do not do well focusing infrared light along with the visible spectrum, resulting in fuzzy, bloated stars. The same is true of many camera lenses. For these types of optics, you can see a large improvement in your images by using an IR cut filter. Besides the beneficial effects mentioned already, filters have a number of other effects on your observing or imaging. The first thing to note is that filters change the scene's white balance. Broadband filters add a magenta hue, oxygen 3 a green hue, hydrogen beta cyan, hydrogen alpha red, and IR pass filters a brownish red color. Some filters are better than others for white balance. For example, multi-band filters give a good color balanced image. For those of you who are imaging, post-processing may or may not be able to completely correct for the hue added to the scene by the filter. Another effect to note is that filters will change your focus slightly because of refraction. Enough that if you change from one filter to another, there is a good chance you will need to refocus. That is why many users like to purchase all their filters from the same manufacturer, so the glass is the same thickness, permitting filter changes without refocusing. Finally, filters add 2 more surfaces to your optical train to have reflections off of, although anti-reflective coatings can help with that. Filter surfaces can also collect dirt, dust, or dew, so yet another thing to keep clean. The final aspect of astronomical filters to talk about is cost. It is tempting to save money and go with a cheaper solution, but quality really does suffer. Cheap filters are prone to reflections, delamination, poor machining, optical distortion, poor optical transmission, and various other issues. There are a lot of filter manufacturers available, perhaps too many. I put them into 5 groups, ranging from premium filters all the way down to filter brands that you should avoid. Astronomic and IDIS are 2 of my favorites in the high quality category. And amongst the good value manufacturers, I have had very good success with Optolong. Well, that brings us to the end of part 2. I would be happy to answer any more questions that people might have on this section before we head on into the 3rd and final part.
I have one question.
Sure.
About the imaging. You mentioned the dark sky category. What do you consider to be, what Bortle class do you consider to be going in that dark sky where, like, saying, taking a picture of Andromeda or the overall Milky Way, you don't need any sort of filter, or you shouldn't use any filter?
Good question. Probably anything better than a 4. A 5, you're starting to near the horizon, probably want to use a filter. A 6, you're definitely going to want to use it, or we'll start to see an advantage. It's sort of it's not a fine line. It's not like on this side of the line, they work, on the other side, they don't. It's more of a gradual transition where you see improving performance as the light pollution gets worse and worse.
So basically, if you're in a, say, a 3 or less, you don't really need it. 4 to 5, you might want to consider it if you're closer to horizon or something like that. Is that what you're saying?
Yeah, and that's for a broadband object like a galaxy or a cluster. On nebulae, I would use a filter regardless of how dark my sky was, because they always improve contrast.
Okay, good to know. Thanks.
Welcome.
Okay, Jim, this is Brian again. You're killing me. It's like I bought a set of LRGB filters. I went with the chromas, So the least, maybe arguably the least critical filters I went with. I've been tormenting myself on the SHO filters and halos primarily. The bargain ones that you didn't mention, the what are they, the Entlias, I guess, which thankfully they're not in stock, so I can't be tempted. I guess they have a history of halos. Is there any, I mean, I look at the filters and go, okay, you got a 3 nanometer or a 3 nanometer filter, you got a 5, you got an 8. And I'm running my primary imaging camera is a 132 refractor. It's a Floral Star, a Williams Optic Floral Star 132. And the little bit of imaging I've done with it with a color camera, I'm just using a UV IR cut filter on galaxies, and I've been pretty happy with it. I'm kind of floating in the 4.5 to 5 Bortle category. So aside from just being proactive and buying the 3 nanometer filters, is there going to be any short-term benefit of those over, say, a 4.5 or a 5 nanometer filter in this Bortle category with that size refractor?
Good question. What's the focal ratio again of your scope?
Unreduced it's 7 and reduced it's 5.
Okay. In the third part of my presentation, I'll talk about something that will be might be of interest. It's relating to how narrowband filters behave with short focal lengths.
Oh yeah, well I have a Hyperstar, so I understand that. Yeah.
Yeah. Okay. Now, whether or not it's worth it to go to a 3 nanometer versus a more affordable 6 or 7. That's actually something that I'm kind of working on right now.
Okay.
And you'll see some of the preliminary results that I've started getting. And it's almost a personal choice, because if you collect enough data and you have a good procedure for reducing the data and coming up with a combined image and processing it, that can make up a lot for the how narrow the bands are on your filters. If you were where I am in a Bortle 9 environment, then I would say 3 nanometers,
yeah.
Sure, go for it. Even though I'm getting very good success with 6.5, 7 nanometer filters. And I'm working on a report right now about that exact thing. But where you are, I don't know if you would see the value in it.
Yeah, and fortunately or unfortunately, the cost difference really between the, say, the Chroma, I can't remember if they're 4.5 or 5 nanometer, and the 3 isn't really that much. But there's always this temptation to go with that value priced filter.
Yes.
I mean, especially when you're talking, say, the Optolong 3 nanometers are a little over $1,000 for the 36 millimeter framed ones, the unmounted. The equivalent Chromas are $2,300 US.
Yeah, I know it's a big difference.
Yeah, and I'm trying to come to grips with, am I getting my bang for the buck out of those, or is that something that, yeah, I mean, how would you, how do you put that on a spreadsheet? How do you put that on a chart and make that decision? Have you found a way to objectively?
I'm trying, and the problem is it means that's a good segue into what I'm going to show you next. Actually,
I'm listening. Then we'll let you go.
Unfortunately, it means somebody has to get all of these filters and test them,
right?
Because the material that's put forward by each of the camera vendors, even the good quality vendors, they're only going to promote, the awesome final product images that people are producing with their filters. they're not going to talk about other issues like, oh yeah, by the way, you can't use this on fast optics, or by the way, you might get halos with this filter, or those types of things. Those are always downplayed.
Well, in all fairness, Agena Astro on their website for the Entlias,
Yeah.
they literally say that you're going to get these halos. If you don't want these
Yeah.
halos, buy these filters instead.
Yeah, I saw that. They did used to say that. And then people
Yeah.
started complaining on cloudy nights and stuff about, hey, I've been getting these halos on these Antlia filters. And then they changed the wording and said, you know, you may get them, you may not.
Right.
Get
And
what
so
you pay for.
when are you more likely to get it? Are you more likely to get it with a triple refractor, an SCT, a certain focal ratio? What triggers that? And is it usually the O3? It seems to be
Yes.
the O3.
It is definitely the O3. I've noticed that in the little bit of testing that I've done, trying to track it down, that it's in exploring multi-narrowband filters. When I break out each of the color channels, it's predominantly
Okay.
the green channel. So
Well,
it's the O3.
And I'll let you continue on this because I don't want to monopolize all the time. To that end, mixing and matching the filters, say if you went with the expensive hydrogen alpha sulfur filters and then went with a cheaper one of those, and then went with the more expensive O3 filter, you have filter offsets, you have automatic, electronic focusing. So that diminishes the impact of that. It'd be interesting to see, is that feasible? I'll let you go.
Oh yeah. Yeah, I would say that it is. Maybe we'll move along. The final section isn't very long, and then if anybody has questions about any of the 3 sections covered tonight, then I'll be happy to answer. So the first area of research is the ongoing race for the best multi-narrowband filter. These filters have become very popular with one-shot color imagers, and also with the electronically assisted astronomy crowd, which I'm a big member of. This has motivated filter OEMs to work on developing the ultimate filter. They have worked to produce filters with progressively narrower bands in order to increase contrast to the max. Presently, there are 15 different models of multi-narrowband filter available commercially. I have plotted them here in terms of the width of their oxygen 3 and hydrogen alpha bands. The dot color denotes the cost of each filter. Although I have tested most of these filters over the past few years, most recently I did a comparison between the top 4 performers: the IDIS NBZ, Optolong L Extreme, Antlia ALP-T, and the Radian Triad Ultra. I made both benchtop spectrometer measurements of these 4 filters and deep sky object image comparisons. My testing resulted in plots such as this. That shows not only how each filter performs relative to the other, but how that performance changes with the optics F ratio. My findings were that the ALP-T was the best all-round performer, and that the Radian Triad Ultra, on average, did not perform significantly different than the much less expensive L Extreme. The topic of narrowband filters and fast optics is my second main area of research over the past year. If you can recall from earlier, an interference type filter's bandpass is defined by the thickness of its layers. Thus, if you change the thickness of the layers, you change the filter's bandpass. Well, it so happens that if light is directed through the filter on an angle, you effectively increase the thickness of the layers. It also is the case that the faster your optics, the steeper the light cone it produces. In other words, light passes through the filter at more of an angle. The net result of trying to use narrowband filters on fast optics is the center wavelength of the filter shifts down, the peak transmission is reduced, and the bandwidth increases. The graph shown here on the left is of an actual 3 nanometer wide hydrogen alpha filter that I measured with my benchtop spectrometer. You can see how the pass bands shifts down and left as the angle of the light passing through the filter is increased. In terms of what this does to how your scope works, it is as if you added an aperture mask. This plot on the right shows what I mean. The curves are my prediction of the effective aperture that results from using a hydrogen alpha filter of varying bandwidth on scopes of different F ratios. Refractors down to a speed of f3 do not appear to be affected too much by narrowband filters as narrow as 7 nanometers. A scope as fast as f4 is probably fine to use filters as narrow as 5 nanometers, and an f5 scope as narrow as 4 nanometers before one would notice any degradation in scope performance. Scopes as fast as f2 are severely impacted by narrowband filters, especially scopes with central obstructions like a RASA or SCT with Hyperstar. Fortunately, filter OEMs have the backs of fast scope owners, as there is a growing selection of pre-shifted filters available for use with fast optics. The center wavelengths of these filters are positioned slightly to the right of the desired nebula emission so that when the band shifts down on fast optics, the pass band is properly centered where you want it. The final area of filter research I've been working on lately is evaluating narrowband imaging filters, sulfur, oxygen, hydrogen, or SHO. This research was triggered simultaneously by Optolong sending me a sample set of their 3 nanometer SHO filters to test, and a friend of mine asking me to evaluate the Chroma 3 nanometer H-alpha filter that he had just bought. In trying to measure the spectrum of these very narrow filters, I learned that I had to upgrade my spectrometer to have a better resolution. It took some time and delicate surgery on my spectrometer, but I am now able to measure filters to a resolution of 0.5 nanometer. This is a plot of some of my measurement results using the newly upgraded equipment. And you can see from the curves here, I've tested IDIS's 2 narrowband filters they have available, hydrogen alpha and O3. They're in the 6.5 to 7 nanometer range. The Optolong 3 nanometer set, SHO set, just a lone Optolong 6.5 nanometer sulfur 2, and then the Chroma hydrogen alpha 3 nanometer. Those are the main 7 filters I've been working with lately. The next step is to test these filters on a camera in the field, which I started doing just this past Monday night using IC1318 in Cygnus as my target. So far, the hydrogen alpha filter results are looking very interesting, showing a clear trend in signal to noise ratio with filter luminous transmissivity. Stay tuned for more on this topic as I collect more data through testing. So that is it. That is the end of my presentation.